As we just mentioned, that distance vector is a wonderful routing algorithm provided it does not suffer from loops. Because if there are loops, then the distance vector updates would be received at a node from various sources. And those sources in turn would also be or could also be connected to each other. A natural consequence to that would be there could be some kind of who started first kind of situation. For that, a problem known as count to infinity problem could arise. In this module, we shall understand how link cost changes could occur and how distance vector updates are created. What are the good news and bad news concepts? We look at the problem, which is the count to infinity problem, and then we'd look at the looping scenario, which is created due to the count to infinity problem. The reference for the scope of this module is Quiroz and Ross. Whenever there's a change in the topology, either some new link is added to a network, some link is removed from the network, the congestion builds on the network, or the bandwidth of a certain link or links is changed, the costs are going to change. The routers, which are connected to each other through these links, would detect the change. They are going to update their routing information and also create the distance vectors. Now, these distance vectors, if there's a change, are sent to their immediate neighbors. Let's look at an example topology in which there are three neighbors connected in a full mesh. That is, all the neighbors are connected to each other as X, Y, and Z. And let's assume that the initial costs were on a link X to Y, the cost is 4, Y to Z, the cost is 1, and from X to Z, the cost is 50. If the link cost on XY changes from 4 to 1, it's naturally a good news because the cost has reduced. How this good news would be updated? At time t0, Y detects that the link cost has changed. It updates its distance vector and informs its neighbors. The neighbors are, of course, X and Z. At the next time instance, t1, Z receives the update from Y and updates its tables. It computes new least cost to X and sends its own distance vector. When Z does so, at time t2, Y receives this distance vector, which is an update. Since according to Y's current information about its direct link to X, the overall costs are not changing. So the distance vector is not going to change. Hence Y is not going to update its own distance vector, and it is not going to send a new distance vector update to its neighbors, that is X and Z. But if it's a bad news, what is going to happen? Again, for the same topology, if the link cost goes from 4 to 60, what it essentially implies is that this bad news has to be sent to its immediate neighbors so that if there is a change in their distance vectors, they should do so. We just saw in the preceding slides that the good news was traveling very fast. But the bad news is going to travel slow because of the to and fro information sharing of distance vectors, and the same question to which I hinted, that who has the correct information and who started first. It can be determined that 44 iterations would be performed eventually before Z updates its distance vector to a cost that is larger than 50. And Z is of course going to do that via Y, because through Y the costs have increased to 61. So Z is going to change eventually in its own distance vector. In order to understand how bad news causes loops and how bad news travels way too slow as compared to the good news, let's look at the same scenario, but this time we look at their routing tables and we see the change they notify to their neighbors through distance vectors. The figure shown to you can be understood as being two parts. The part above is actually the information that is between the neighbors, such as if you look at top left, it is the distance vector of Y, that is the cost from X to Y is 4 initially and X to Z is 6. This is the information that is stored at node Y. When there is a cost change, you see here that X to Y cost is now changed to 60. This change is to be notified, but since Y also knows the fact that Z is connected to X through another path, so Y, with such increase in direct cost with X, chooses to route its traffic through Z. And this is all what we shall see as a loop causing situation, and it is going to follow in the next couple of slides. Let's start on a time scale that is shown to you here. At time t0, Y detects that the link cost has changed from 4 to 60. Y computes its minimum cost path from itself to X. Now it is going to send it through Z. Of course, we understand that this new cost via Z is wrong. And why is it so? Because initially the cost from Y to X was direct. Since the nodes do not have the picture of the whole topology as we do have, and they are just restricted to the information sharing between the neighbors, so as it is natural, the only information that Y has is that its direct cost to X is Z, and Z has last told Y in its distance vector, when Z sent its own distance vector to Y, that Z could get to X with a cost of 5. So Y assumes that since Z already has a path to X, why not route through Z? So in order to get to X, Y would now route through Z, fully expecting that Z will be able to get to X with an additional cost of 5. So in order to get to X, Y would now route through Z, fully expecting that Z will be able to get to X with a cost of 5. But at time instance t1, we already have developed a routing loop. In order to get to X, Y routes through Z, but Z in its own distance vector had the distance vector which was based on the path to X via Y. Now this routing loop is a black hole in its own self. A packet arriving at Y or Z as of t1 will bounce back and forth between these two nodes forever or until the routing tables are changed. And this iteration, as we can convince ourselves, would take 44 steps.